opportunity to present this talk in Prague, and thank you for coming. I would like to present some first results of my PhD study. I work on an Eclipse and binary stars with spots. There are some programs which are often used for modeling, like Binary Maker, Phoebe, and others, and they all are based on the Wilson-Deviney code, which allows to compute light curves for user-defined sets of the parameters. However, the main aim to determine parameters from observed light curves. This problem needs to determine many parameters and thus is ill-defined. An existing program allows to determine parameters of only one spot with an assumption that it is a circle with a constant temperature parameter inside. Of course, these are simplifications, but they are typically in the literature. A rapidly increasing number of observations allows to study changes of the spot parameters, but needs fast and effective methods and programs. An existing program, which was developed by Professor Stanislav Zala from Krakow Observatory, allows to make models for multicolor observations. However, if modeling observation from different dates, one will generally get different number of parameters, not only for spot but also for star. Physically is not realistic because star can't change parameters from year to year or even from night to night. Thus, in future, we plan to make a program which allows to make statistically optimal modeling as constant star and changing spot. So our aim to find the fastest way to determination parameters of eclipse binary stars. To test an existing methods of parameter determination, we use for different types of functions. Physical model, simplified test function, and phenomenological modeling. For physical modeling, one has to determine 15 different parameters. They are listed at the slide. Also listed the best fit parameters for the star IM Leo. Of course, the number of parameters is large, so some values were fixed using additional information like spectral observations and color indices. Here we see the period was determined from long-term photometry of other outers. With this, for such a short period, the orbits are typically circular, so eccentricity was fixed to 0. In this case, the periastron is everywhere, so this value we fixed to 90 degrees. The gravity darkening coefficients was taken from theoretical works. The mass ratio was determined by other authors using spectral observations of ratio velocities. Also, theoretically was taken albedo, and the last fixed parameter is temperature T1. Because light curves are dependent on the temperature differences, we must fix one of these parameters. Other 4 parameters were fixed or were determined using Monte Carlo method. Here we plot points in the parameter diagrams, and there are 100,000 computations. For each new computation, the fixed number of best rated is redetermined. For smaller number of computations, the points as a diagram uniformly distributed. With an increasing number of computations, the bad points are thrown away, and the better points concentrated into small regions toward to minimum. But bad points still computed, and we can say that this method is slow and needs days for computations. So common problem, estimate of the parameters may be dependent, so We made our test on another function which is similar in the behavior to a test function used for modeling eclipsing binaries. Working conclusion, the best solution can be not single, it can take some region in the space of parameters. And here we see 2D simplified test function. There are two local minimums. There are two local minimums, you maybe don't see, but believe me, it's true. Parameter alpha tending to 0, and we take line as a solution. In other words, we take infinite number of solutions. At this animation, we can see best 10 and 100 points after 100,000 of computations. And we see fast converges to green line, and very slow converges best points to minimum. Here we see dependence of the number of computation needed to get deviation f of the single from exact minimums. The lines are for 1, 2, and 3 parameters, and we see how drastically increased number of computations needed to get fixed accuracy. The upper line show dependence of the number of computations needed to get a better point. Here we see dependence of the test function on the parameter alpha. The right figure corresponds, show the right figure divided on the 3 different zones. The zones corresponds best methods which we use. And in the red zone, this method is conjugate gradients, and in the zone blue and green, this method is steepest descent. Here listed other methods which we use for our tests. While testing other methods, we need function which computed relatively fast. So we applied simplified physical model. It differs from the model of Wilson-Duvigny by an assumption spherical symmetry. This can be used as a first approach to Algol type stars. Additionally, we neglect limb darkening. But we can say that this model is widely used for education. Here we see at the left figure, we can see levels of fixed parameters of test function, and here we also see the best points concentrated in the small region toward to minimum after the Monte Carlo method. The last part of my talk devoted to phenomenological models. These models are effective for majority of stars for which not enough observation to make physical model. Sometimes these models are very simple, but anyway they are used for analyzing hundreds of stars. Here we see approximation light curve by parabola. Obviously we need the better approximation. The typical approximation of periodic function is a trigonometrical polynomial called Fourier series. Here we see example of this approximation. One may see that abrupt changing of brightness need big number of trigonometrical polynomial, and of course big number of parameters. Once more, there are appearance some waves at the curve. We prefer special shape of eclipse. Here we see approximation of 11 parameters, and this corresponds to trigonometrical polynomial of order of only 5. This model effective for Algol type stars with a narrow minima, but also can be applied to EB and DW types of stars with smooth variations. Yes. Here we see dependence of the best fit light curve on the minimum half-piece and the shift of the minimum, and also dependence of the smooth light curve on the parameter describing the profile of the primary and secondary minimums. So work is in progress, and you can see our future plans, application developed programs, and improvement existing programs for a case of sports which migrate from season to season. Thank you for attention.